Okay, our next topic is kinematics, which is all to do with graphing the way that objects are moving. So you can also sometimes refer to this as talking about speed, velocity and acceleration. So just to get your head around what we're going to be doing, by the end of this you need to be able to calculate displacement, instantaneous and average speeds, velocities and accelerations, and be able to represent those graphically. Find velocity from a displacement time graph, find acceleration and displacement from a velocity time graph. So mostly we're just going to be looking at the graphs. But to do that, we need to make sure we've got our terminology straight in our head. So let's start with distance and displacement. Now, what you will notice is that when I do these, in the brackets, you've got a symbol here. So here it's an X and here it's an S. So X is the shorthand symbol for distance, S is the shorthand symbol for displacement. It's just to help us keep track of what we're doing, and it lets us be lazy. So I can just put the letter, and that is what I'm talking about then. Anyway, we'll start with distance. Hopefully you know a little bit about these two terms, but I just want to be sure that we've got them really firmly in our heads. So distance is just the length of the path that the object has moved. It's a scalar quantity and it's measured in meters. Displacement is to do with how far away an object is from its starting point and the direction in which it is away as well. It's kind of like the crow flies distance. So it's just the straight line distance between the two, and we do care about the distance, the direction, sorry. Finally, it is a vector quantity and it is measured in meters. Okay, next up is speed, which we give the symbol V, and hopefully you already know how to calculate speed. So I'm going to talk about average speed as being the distance changed divided by the time taken. So if I was going to write that as a symbol, it would be the average speed equals the change in x divided by the change in time. Again, it's a scalar quantity and it is got the unit of meters per second. Now, if I want the instantaneous speed, that's going to be the rate at which the distance is changing per time. So that's v equals delta x by delta t. Unfortunately, Windows is not very good at doing deltas nicely, so I've just got lowercase d here, but it means the same thing. Basically, what I'm talking about is that it's the gradient at that point in time on a distance against time graph. So if I was interested in the speed at 2 seconds into the motion, I'd look to see where the line was at 2 seconds, draw a tangent, measure the gradient, and that gradient would be dx by dt, and that would give me the instantaneous speed. So it's just the speed at that exact moment in time, whereas the average speed is looking at the speed over the whole time. Next we've got velocity, which also has the symbol v, which might seem a little confusing, but by context you should always know which one it is anyway. So for this, average velocity is just displacement change over time taken. So for this one, I've got delta s by delta t. It's a vector quantity. It's the same as the displacement change. The direction is the same as the displacement change. And my unit is going to be meters per second. And again with this one, the instantaneous velocity is found the same way in essence as the instantaneous speed. The only difference is I'm looking at a displacement against time graph, and I would look at the gradient at that point in time, and it's just the delta s by delta t, which is the gradient at that specific point in time. Right, next up is acceleration, which has the symbol a, nice and easy to remember. The average acceleration is just going to be the change in velocity over the time taken. Note it is velocity, not speed, so that means that acceleration is a vector quantity, and the direction will be the same as the change in the velocity. And the units are meters per second squared, so that's meters per second per second. And once again, instantaneous acceleration is the rate of change of velocity with time. So this time I'd find the acceleration by looking at the gradient on a velocity against time graph, and I'd look at the gradient at a specific point in time, and that would give me the instantaneous acceleration. So a couple of things to just note that will make life a little easier later on. When I'm calculating the change in velocity, obviously I'm sure you know that I would do that by doing the final velocity take away the initial velocity. Well, as I mentioned, we're lazy, so we tend to give those symbols. So final velocity has the symbol v, and the initial velocity, the starting velocity, is given the symbol u. So that gives me a slightly different version of the equation for average acceleration, which is v minus u over t. You will see this equation quite a lot, and we will do lots of funky things with it later on. Now, another little definition, uniform acceleration. We're not specifically talking about this right now, but it will come up later, so it's good to have it in mind. Uniform acceleration just means that the acceleration is constant for a period of time. So if it's constant acceleration, that's the same as saying uniform acceleration. And that is a very special case, and we can do some very interesting maths when we have uniform acceleration. So keep your eye out for when that's happening. Now, the other term I want to define is deceleration. Deceleration is a term that people often have a lot of trouble with. Deceleration does not mean the same thing as negative acceleration. So if you have an acceleration that is negative, that is not necessarily deceleration. Deceleration is where the magnitude of the velocity is decreasing with time. The negative sign tells you about the direction that that is happening. So you could have an object with a negative acceleration that is getting faster. So that would not be deceleration. So you've got to be really, really careful with that. If in doubt, I would probably try and avoid using the word deceleration, because there's a very good chance you're going to use it incorrectly. So just really think about what the numbers and the sign are actually telling you. Quite often, negative signs are not telling you that something is smaller than 0. They are often telling you something about the direction or the type of thing that you are looking at when we're talking about it in physics. So you're just going to have to think really hard about that. Okay, so let's have a look at some of these graphs then. So first up are distance-time graphs, which you should be really familiar with anyway. So for a distance-time graph, the gradient of a distance-time graph will give you the speed. So if I wanted to find the instantaneous speed of this object at point y, so the speed at y, I would look for the gradient of it at that point. So as you can see, I've drawn the tangent, and I'm just going to find the gradient of that triangle, which is PQ over QR. So that would give me the instantaneous speed. If I'd wanted the average speed, what I'd do is say, if I want the average speed over the first 40 seconds, well, my time would be 40 seconds. I'd look at what distance it goes in 40 seconds. That would be 120. So for the average speed, I'd do 120 divided by 40. So that would be the difference between your average and your instantaneous. So if we just go through with the calculation for the instantaneous, it would be 7 meters per second. Pretty easy, right? So displacement time graphs, this time the gradient is going to give me the velocity. Here's another one. So this might show you how an object's displacement changes as I throw it up in the air. So it goes up and then comes back down. So notice that I've got my maximum velocity up at the top, and I've got my maximum negative velocity up at the top when it's going back in the opposite direction. Okay. Nice and clear like that. Oh, sorry, I said maximum. I meant minimum velocity because it's got the minimum gradient. I'm sure you all spotted that instantly, right? So I've got my maximum velocity right here at the beginning because it's going its fastest up here. It slows down till it gets to 0, then it starts to go back in the other direction, speeding up again. And if you notice, it is a nicely symmetrical curve. It's a nice parabola, in fact, a shape that we're going to talk about quite a lot. So if I wanted to know what the initial velocity of the object was, that would be its instantaneous velocity. I'm going to stick a gradient on there. I'm going to draw a tangent and calculate the gradient. So use those numbers and I'll come out with something like 10 meters per second. Okay. I can do exactly the same sorts of things with the velocity time graphs, and we're going to look at those a little bit more when we're in class, but the principles are all exactly the same. Now, yes, that's it. That's everything. Okay, so any questions? Make sure you ask when you see me, and that's it really. Should be pretty straightforward, this one.